Hey everyone, welcome to another ALEKS tutorial. In this one, we are going to be deducing valence electron configuration from trends in successive ionization energies. That is a mouthful, but let's take a look at the problem. So it says the first 5 ionization energies, IE, which is ionization energy 1 through IE5, of a periodic 3 element have the following pattern. So we have energy 1, 2, 3, 4, and 5, and we want to find out what this element is. So we're given a couple different hints. The obvious hint is that our first hint is that it's a period 3 element. So that means if we look at a periodic table that our element is going to be in period 3. So that's simple enough. It's a period 3 element. We're given one other hint that's not explicitly stated, but if we look at the graph, we can see that our 4th ionization energy level is much higher than 3, 2, or 1. So what does ionization energy even mean? Well, the ionization energy is essentially, to put it simply, it's the minimum amount of energy required to remove an electron from the atom. So think about an atom. This is its nucleus, and around the nucleus we've got these shells of atoms that are all filled up. And then we have this outer shell that we call the valence shells. And there's an electron spinning around in this outer shell. And it's by itself. These inner shells here, the ones in here and the ones in here, they're all full, but in the valence, there's just one electron out here. And it's rotating around this atom, essentially, because it's attracted to the positive center of the atom. However, this outer electron is going to experience a lot less of a force than, say, this inner electron, which is very close. So the attraction between this electron and the positive nucleus is going to be very strong. And so when you have these valence electrons, the amount of energy that it will take to steal one of these electrons away will be relatively low compared to the amount of energy it would take to remove this electron and steal it away. So, using this principle, we can see that the first electron that we take away, it's pretty easy. The energy level is relatively low. The next electron we take away is still relatively low. A little bit higher, but still low. Same with the third energy. Not too much energy is required to take this electron away from the atom. However, once we reach 4, it suddenly jumps up by several times. I mean, you could fit several It's like 3 times more energy that was required to remove level 4 than level 3. So what does this tell us? Well, it tells us that these levels represent 3 valence electrons. So going back to our little diagram, that would mean that essentially there are 3 electrons in our valence shell. And so these electrons are going to be pretty easy to just snatch away from the atom. However, once all of these electrons have been removed, then we start trying to remove these what we call core electrons or inner electrons. And those are a lot more difficult to remove. So when we're talking about electron configuration, you'll remember that we have something called the noble gas electron configuration. And the noble gas electron configuration is not only just a great way to write shorthand electron configurations, but it's also a good way to tell us what our valence electrons are. So we're told that the element that we're looking for is in this period 3. So that means that the noble gas that is going to correspond to an electron configuration within period 3 is going to be neon, which is 10 electrons. So you would start off with neon. And then, after neon, which just in case, neon is 10. So neon represents 1s2, 2s2, 2p6. So our noble gas starts with neon, and we're looking for 3 valence electrons. So all we need to do is just add on to our noble gas configuration with 3 more electrons. So what comes after 2p? 3s. And we need 3 total, so this would be 3s2. And then what comes after 3s2? That would be 3p1. And so this is what element we're looking for. So this corresponds to 13 electrons, and it's not specified that this is any kind of cation or anion, so with 13 electrons we can assume we also have 13 protons. So whatever has an atomic number of 13 is the element we're looking for. And that, in this case, is aluminum. So aluminum is the element we're looking for. And that is your answer. And just to add on to this, just in case you didn't know what came after neon, just so you don't have to write out the configuration of neon, in our last video, you'll remember that we talked about the different areas of the periodic table that correspond to different subshells. So groups 1 and 2 correspond to the S subshell. All of these groups correspond to the D subshell. And all of these groups correspond to the P subshell. So if we want to know how to write the electron configuration for aluminum, all we would need to do is take the preceding noble gas, neon, and we're in period 3, so we start with 3, and we know that this group contains our S1, and this group contains our S2, and so we just need to add on 3 electrons, so this is 3s2, and then 3p1. 3p, these are all the p1s, and that's a little trick you can use to write the noble gas configuration very quickly without having to write out the entire electron configuration for the noble gas beforehand. So I hope that helps, and that's it for this video. Thanks for watching.